Good afternoon. My name is Kurt Loit, and I'm a software developer for NASA at the Kennedy Space Center in Florida. And it's my honor to speak to you this afternoon about NASA's ant-inspired swarmy robots. That is a really big screen. I know we just got back from lunch, and everybody probably wants to cuddle up and take a nap. So I'll do my best to keep this talk exciting and entertaining and try and keep you all from falling asleep like that guy. Let me take just a quick minute to introduce myself, since I'm not a famous speaker or anything. There's my name and the pronunciation. That's not how they pronounce it in Germany, but that's the Americanized version, Loit. I have a wife and 2 boys. I've been a NASA software engineer for 25 years now. Most of that time, I've been working on software for command and control systems at NASA. And those command and control software is the software that runs in the firing room, and the firing room is the place that monitors and controls the rocket and all the support equipment that supports the rocket. I grew up loving computers and software. I started writing software at a young age on my Apple IIe, which still works, by the way. It's in my garage. I play with it every once in a while. And I learned to program using a program called TurtleTracks. Raise your hand if you've ever heard of TurtleTracks or used it to learn how to program. Awesome. I'm surprised how many hands went up. In recent years, I've started working on software for several robotic systems at NASA, and I'm going to talk about some of those. And since I work for NASA, let's start about talking about NASA's whole reason for existence. NASA's known for space exploration, obviously, but what is the end goal? What is NASA's purpose or vision? We reach for new heights, and we reveal the unknown. And we do this for the benefit of all humankind. So, reaching for new heights covers all the exploration of outer space and other planetary bodies that we do. Revealing the unknown covers all the science that we do, both on Earth and in outer space. And for the benefit of humankind, that makes sure that we don't just think of ourselves. Everything that NASA does is basically for everyone's benefit, not just for NASA's own benefit, and not even just for America's benefit. Everything that NASA does benefits the human race. So let's talk a bit about what NASA's focused on right now. We're working on sending humans to Mars. But why? The official reason that we want to go to Mars is because it's a rich destination for scientific discovery and exploration. It's like Earth in many ways. It has an atmosphere, although not a breathable one. It once had flowing water, and it might hold evidence of past life. The unofficial reason, though, is Mars is really, really cool. But sending humans to Mars is going to be different from our earlier missions that we sent humans to the moon. The Apollo moon missions were basically very short camping trips. We launched those missions carrying everything we needed for the trip there, which took 3 days, and for the stay on the surface, which took from a few days early on the program to a week or so later in the program, and also for the return trip home, which took another 3 days. And carrying everything that we need for a mission, that's just not going to work for longer, farther human exploration missions. We're going to have to live off the land. And in the context of space exploration, living off the land is known as in situ resource utilization, or ISRU. ISRU is really exciting because it's a way to reduce the mass and the cost of space exploration. And really, it's just not going to be an option. ISRU technologies are going to be needed for missions where astronauts will live, work, and be productive on another planet. There's just no way economically that we'll be able to pull off those missions without living off the land. We are just now starting to plan for and experiment with ISRU technologies off our planet Earth. Resource Prospector on the left is going to the moon in the next several years to dig 1 meter down and prove that we can pull water out of the lunar soil. MOXIE on the right is an ISRU experiment flying on our next Mars rover in the year 2020, and MOXIE is going to prove that we can pull oxygen gas out of the Martian atmosphere, which is mostly carbon dioxide. So, as you can see, NASA is gearing up for ISRU missions that'll prepare the way for future human missions and even for long-term human colonies. All of our missions so far have sent one robot to just one location, which has been fine because all those robots are designed for a very specific type of mission, and they've usually exceeded their mission requirements, and they've gone far beyond their warranty. But NASA researchers were starting to consider the benefits of swarms of small robots, small and relatively inexpensive robots, in order to perform tasks that would be more applicable to a distributed system of robots. So where did the idea of swarm robotics come from? Probably Hollywood, but swarms of robots are often inspired by nature. And it turns out that they have some pretty great features. They're robust to individual failures, they're adaptable to changes in environments, they're highly scalable, they're relatively inexpensive, and they're efficient at distributed tasks. And when you think of it, I suppose the best way to accomplish a task has already been perfected by nature. Take ant colonies, for example. There are often thousands or even millions of individual ants in a colony, and there's no foreman, there's no blueprints, there's no one actually in charge. A lot of people think that the queen ant is in charge of the colony and tells the other ants what to do, but that's just not true. Her only job is to lay eggs. All the other ants are just born knowing what to do. Now, this photo that you're looking at is showing a huge ant colony in Argentina, and this nest is abandoned, and these scientists in this photo are performing an archaeological excavation and study of this nest. That's pretty cool, huh? These large ant colonies, they build a huge and complex nest that supports the entire ant colony. They find and gather food and water enough to support the entire nest. So how do such tiny ants with such tiny brains accomplish so much? Well, scientists and researchers decided to find the answer to that question. Dr. Melanie Moses and her team at the University of New Mexico studied these ant foraging behaviors, which is the behavior of searching for food and bringing it home to the nest. And part of the research involved studying real ants in the wild, and they took detailed notes on how the ants behaved when searching for food and bringing it home to the nest. And these are photos of some of Dr. Moses' team and the desert seed harvester ants that they were studying. Those red dots are seeds, which is the food that the ants were out searching for. And the ant on the right is actually carrying a seed back to the nest. So after studying the ants in the wild, Dr. Moses' team modeled the ant behavior to try to understand how these biological foraging networks scale to large numbers of agents. And so this state diagram describes the flow of behavior for one individual ant. And Dr. Moses' team was able to reduce this seemingly complex ant behaviors down to this relatively simple flowchart. Here's an example of the path of an individual ant as it goes through these different behavior states while foraging. So the ant starts at the nest and travels to a search area. And the ant searches pretty thoroughly in that area for a while. And if it doesn't find anything in the immediate vicinity, its search path actually changes to what is called a biased random walk, which covers some ground, but it still has some randomness embedded in it. And if the ant actually finds food, it takes that food straight home to the nest. It doesn't go back over the trail that it took to get there. How does the ant know where home is? That's a whole nother research project. But this is just one example, and there are a lot of different decisions that are made along the way that can slightly change these basic behavior steps. One of the really cool parts of ant behavior is the way that they leave chemical pheromone trails on the ground in order to tell the other ants in the colony about a large stash of food that they need help gathering. This indirect communication strategy allows the ants to recruit lots and lots of help without requiring any sort of direct peer-to-peer communication. So this strategy can actually scale to large numbers of ants, and that's pretty exciting. Dr. Moses told me that she got interested in this area of research while she was living in Costa Rica, and she witnessed leafcutter ants in the rainforest there, and she considered the similarities between physical networks of ants and the computer networks that she was studying, and she wondered if it would be possible to scale these computer networks or multi-agent systems using biologically inspired networks. So after modeling the ant behaviors using simple equations, Dr. Moses' team programmed these ant behaviors into a computer simulation. And the behavior and efficiency of the simulated ants wasn't quite correct at first. There were some things about the computer simulation that they built that made it not work the exact same way as the real ants did. An example of that is the real ants sometimes got near a piece of food, but they didn't always notice it. So the algorithm on board the real ants was not perfect. But the computer simulation always saw the food whenever the simulated ant was close to it. So the team added some probabilities and some chance to their simulation, which made it act a little less perfect, made it act a lot like the real ants. So here's some footage of their computer simulation executing. And if you watch it closely, you can start to see some of those behavior patterns that I talked about earlier. You can see the little simulated ants going out from the center, looking for food, finding it, and bringing it back to the center. This simulation also shows the pheromone trail that the simulated ants are leaving. It glows green, and it kind of comes out from the center slowly out towards the pile of food. The green glow gets stronger and stronger as more ants reinforce that trail. It's pretty cool stuff. There you can see the pheromone trail starting to come into view there. So after modeling and simulating the ants, the team took the next logical step, which was to test out their ant behavior algorithm on a swarm of real robots. They created these small, inexpensive ant-inspired robots. They called them the iAnts. The main onboard processor is an iPod, hence the name iAnt. And it also gives you an idea of their size, since their overall length is about the length of an iPod. The iAnt also has an Arduino microcontroller on board that interfaces with the sensors and the motor controller. These robots use the ant-inspired behavior algorithm that I just described in order to search for barcodes that the team distributes on the ground. And these robots pretend to collect the barcodes by keeping track of the unique identification barcodes that they've found. And these robots pretend to take the barcodes home, and they can only carry one barcode at a time, just like real ants. These robots also emulate the indirect communication scheme of pheromone trails that I mentioned earlier. They do this by communicating with a central server about an individual trail that leads towards a stash of barcodes, and then all the robots query that server for this trail information each time they arrive home. These iAnt robots are able to find and collect resources similarly to real ants, and they perform the task using cheap and error-prone sensors, which is really cool. With minimal processing power and minimal memory, and no peer-to-peer communication at all. So, what's the point of researching these ant foraging behaviors, though? Well, that's actually an important problem to solve in swarm robotics because it generalizes to many real-world applications, like finding, collecting, and disposing of hazardous materials or mines in a minefield, or finding and collecting natural resources, or search and rescue missions after a natural disaster, or environmental monitoring over a wide area. So these are reasons why scientists tend to study these types of behaviors and systems. I skipped past an important feature of the computer simulation and also the iAnt robots. The University of New Mexico team, they created a genetic algorithm to optimize the foraging efficiency of this system. And a genetic algorithm is a method for solving optimization problems based on natural selection process. And it mimics the theory of biological evolution. So the algorithm repeatedly modifies a population of individual solutions until a convergence occurs. And it basically evolves over lots and lots of generations the most efficient behaviors for the system based on environmental conditions and other parameters. For example, the genetic algorithm suggested increased communication when the resources were more clustered or tightly packed. And conversely, the genetic algorithm suggested less communication and more individual memory of the robots when the resources were less clustered and more loosely packed. So the genetic algorithm is that's just one simple example. The genetic algorithm is pretty neat, and it probably warrants an entire 45-minute talk, but that's not what this presentation is about, so we're going to move on. So my ISRU research team at NASA, we found out about these iAnts, and we considered how they searched a large unmapped area for food and brought it back to the nest. And it made us think about how NASA might need to search for ISRU resources on the moon or on Mars someday and bring those back to a central processing plant. And we realized there might be some mutual gains if we work together. So we teamed up with Dr. Moses and her team at the University of New Mexico. And our goal was to add some ISRU features to their iAnt system and find out if an ant-inspired system of robots, along with this genetic algorithm that evolves the robot behaviors, might translate into our domain of finding resources on the moon or on Mars. And so the NASA Swarmies were born. So with this new Swarmy robot platform, we improved on the earlier iAnt platform. It's more rugged, it's a bigger chassis, it has more ground clearance, it's capable of operating outside without getting stuck. We used a dedicated single-board computer instead of the iPod, and we improved localization, which is the robot's ability to know where it is in 3D space. We improved obstacle detection, we improved the onboard camera. These Swarmy robots, since they're so giant on the screen, I need to give you some context. These Swarmy robots are about the size of a remote-controlled car. And just like the iAnts, the Swarmies are very focused on using only commercially available parts and keeping the cost very low. Because when you're designing a swarm of robots, the cost per robot needs to be minimal or the mission won't be affordable. So all the parts that make up these robots can be purchased from online hobby robot vendors, and we did 3D print a few of the pieces like the camera mount. We also utilized a robotics framework and a modular software design, both of which have been used on several projects, several internal robotic projects at NASA that I've worked on. And this encouraged lots of code reuse between these different projects and allowed some rapid prototyping on several projects. So we are focused on ISRU research, as I mentioned. And so the main thing we did with this Swarmy project was we added features to the ant-based behavior algorithm and to the genetic algorithm so that features that are applicable to a future NASA ISRU mission. So one thing we did was we added obstacles to the environment, which were not part of the original iAnt system. And we also added the concept of robot battery charging back at the base station. And for this project, we actually simulated the battery charging internally in software and didn't actually drain and recharge the actual onboard batteries. So here are some close-up photos of the hardware. It's a fairly straightforward hobby robot. After all, the magic of this project is mostly in the genetic algorithm and in the onboard ant-inspired ant behavior software, but I will quickly go over some of the details of the actual hardware because it's cool. These things, they look like toys, and they are kind of fun. It was fun to design them and fun to operate them. This robot, but they're not toys. They're a very serious research project. We have to keep telling people that because they look at our project and they're like, oh, you get to play with toys. No, it's research. So the hardware. This robot has a common four-wheel skid steer design. So the wheels, they don't actually steer left or right like your car's wheels. They only rotate straight forwards and straight backwards. So if you want to turn the robot, you command the left wheels forward and the right wheels backward, and it rotates or vice versa. It just spins in place like a tank. The robot has 3 sets of ultrasonic sensors, and those detect solid objects or obstacles in front of the robot. It also has a global positioning system or GPS receiver in order to keep track of its location in 3D space. Remember, this robot is not designed to operate on the moon or on Mars, where we don't have GPS. This is a ground demonstration research project. A robot that would operate on the moon or Mars would include a different type of localization system that's designed to work in that environment. The robot also has an inertial measurement unit, or IMU sensor, and that keeps track of the orientation of the robot or which direction it's pointing in 3D space. The robot has a consumer model USB camera, which, when combined with a barcode library, can recognize barcodes and read their unique IDs. And for wireless communication, we went with a common off-the-shelf USB Wi-Fi dongle. Again, not exactly the hardware you would use on Mars, but it works great for our purposes because these robots were designed to operate outdoors on a paved parking lot within about 100 meters of each other. This is a picture of version 2 of our Swarmy robot platform. It's an improved version, and it's more capable than the first version, but I'll talk more about version 2 later if I have time. So on board the Swarmy robots, we have a small credit card-sized computer that runs Ubuntu Linux. One of the reasons we chose Ubuntu is because we wanted to use a robotics framework called the Robot Operating System, or ROS, and ROS prefers Ubuntu. Plus Ubuntu is just really cool. ROS is not actually an operating system. It's poorly named. Actually, it's a really cool name, but it's misleading. ROS is an open source framework for creating robot behavior software. It comes with robot tools and robot libraries, robot data types, robot conventions. It comes with a nice little inter-process messaging system. So it's really great for this application. It handles a lot of the overhead, and it simplifies the task of creating your high-level robot behavior software versus creating the whole stack from scratch. All right, this is a very, very high-level block diagram of our application software. The green blocks are the robot hardware, or they're the simulation which simulates the robot hardware during our development. And the blue bubbles are the major features of the software, but are not necessarily the standalone executables. And the arrows point out important data or commands that are passed between the components. And these bubbles on the left are actually executing on our Lander base station, which is a common laptop with a Wi-Fi connection to all the robots through a consumer Wi-Fi router. So if we focus on the top with all the sensors, the raw ultrasonic data on the left there is read in by our obstacle detection module, and it turns that raw data into very simple flags that are easy to react to. And then on the camera side, the camera stream in its raw form is read in by our target detection module, and it turns that raw data into simple flags again that are very easy to react to. And then on the far right, both the IMU raw data and the GPS raw data are read in by our localization module, and it merges and it stuffs that data into a common robot data type, which describes the robot's location in 3D space. All 3 of these modules are basically just data processing or data translation. The real magic happens in this big motion control module. That module takes in all this information along with user configuration and the robot mode from the laptop. And it decides how the robot's going to react physically, and it commands the onboard motors of the robot. And so all the ANT-based behavior that I talked about earlier, all that logic is inside this motion control module. And it's mostly made up of a big state machine of ANT behavior, and each state has its own subtleties and complexities. For example, here's some pseudocode for the home state, which is the starting point for the robots, and it's also the ending point after a round trip of searching for resources and coming back home with them. The home state has the option of starting robot charging if that's needed. If charging is not needed, the robot has the option of returning to the resource site that it just came from. And that decision is actually made earlier when the robot actually finds the resource. If it does not want to return to the prior site, it'll check to see if a pheromone trail exists, and then it'll follow that trail if it exists. If there's no pheromone trail, then the robot will just pick a random heading, and it'll drop into the travel state, which is the next state. Here's pseudocode for the searching state, which actually occurs after the robot travels out from home to the search area. This state basically looks for barcodes while random walking. That's the summary. There is a small probability, a roll of the dice, that it'll give up searching and it'll return home and start all over again. It does have to stay within a digital fence that we've set up in the system, and it does have to avoid obstacles while searching. So initially, during a search, the randomness of the robot's turns are highly sporadic, and the robot doesn't end up traveling very far from the search area, and that's how it searches an area very thoroughly. But over time, if nothing's found, the random turns actually settle down a bit, and the robot ends up in a biased random walk, which I mentioned earlier. And that's made up of random turns that are kind of sort of constrained within a cone. You could think of it that way. So the robot kind of takes off in a direction searching, but with some randomness to it. All right, let's talk about the simulator for a minute. The simulator that's mentioned in this slide is not needed on board the robots. It's used offline in our development machines to simulate the robot hardware so that we can develop the code and test it without the overhead of the real robots. A physics-based robot and world simulator actually comes with ROS, but it's also a standalone open source package. It's called Gazebo. And we relied really heavily on Gazebo, along with some user-defined Gazebo plugins that simulate the various sensors of our robots. Gazebo made it really easy to create detailed working 3D models of our robots, complete with the onboard sensors, including ultrasonic sensors, IMU, GPS, camera. And Gazebo includes plugins to listen to the motor commands and react appropriately to them with wheel torque on those simulated wheels. It's also easy to create 3D environments for our robot systems to interact with, including the barcodes and the obstacles or anything else you can dream up. The 3D models for pretty much everything in Gazebo, those are defined and configured using fairly easy to understand XML files. So it's a very simple development environment and testing environment. So development and testing for our project progressed as you might expect in small baby steps. We started by writing individual small ROS nodes or executables, and those performed very simple tasks and had very simple inputs and very simple outputs. And so we did this work on our developer workstations, not on the robot's onboard processors. We used the built-in ROS data types for all of our inputs and outputs, along with the ROS messaging system, the interprocess communication system. And so we tested these small units of code using the ROS utilities to stimulate those inputs and look at the outputs. And there's a very simple ROS command line tool and a simple graphical user interface that can publish these ROS messages on demand for unit testing. And also on the output side, there's a very simple command line tool for looking at the output. There's also a very simple GUI that subscribes to these ROS messages and shows you the raw data inside. So the next step in our baby step development technique process was that we chained two individual ROS nodes together and verified that they worked together appropriately, and we still used the ROS utilities to stimulate the first inputs and look at the very last outputs in that chain. And we just added nodes one at a time until all the code was running simultaneously, all except for the endpoints or the drivers, which actually needed to interact with the robot hardware. Remember, we're not running this on the onboard computer yet. So during this process, we found bugs, integration issues that we hadn't considered during this process. At this point, the next step was to run the same integrated code that we just saw, but instead of stimulating the inputs with these command line tools or very simple GUI tools, we ran the whole thing inside the Gazebo simulator. And so Gazebo automatically stimulated the sensor data appropriately based on the environment that that simulated robot was driving around in. So the camera data actually showed the world that the robot was driving in. The ultrasonic data, it showed obstacles that we place in the simulated world. And Gazebo moved the robot around to that environment appropriately according to the drive commands that were published by our motion control module there. And so this step showed us some of the bad assumptions that we had made about some of the inputs and some of the outputs. An example of that is we used a floating point number between -1 and +1 for our commanded robot drive motor speed. And we knew up front that the motors that we chose for these robots, we would probably never operate them at full speed because they're pretty fast. They're remote control race car motors. You know, they go pretty fast. We didn't need our robots to go that fast. So we assumed, we picked a speed, a top speed in our code. When we put it into Gazebo and tested it in Gazebo, Gazebo's actually simulating the wheels, the axles, the bearings, the motors, the masses of all these parts on the robot. It simulates the friction between the robot's wheels and the ground. And the speed we chose was still way, way too fast. We had to send teeny tiny little commands to these motors in order to get the robots to operate in a way that we needed them to, and a speed that we needed them to operate in order to do this ant behavior. So running this in Gazebo helped us correct some of our assumptions about the robot hardware, even before that hardware was even built and operating. So the simulation was completely saved us a lot of time and effort. The simulation also helped us realize some of the issues we were going to have with our physical robots, like the infamous bug trap. And a bug trap is a common robotics problem whenever there are walls or obstacles that kind of close in on themselves, like a cave or a room with a small opening. And it's pretty common in the robotics field for a robot to wander into a bug trap and have difficulty getting out. And we used kind of a naive obstacle avoidance algorithm on this project. And that allowed us to rapidly deploy, but it also made the robots susceptible to bug traps. And solving the bug trap problem is a whole other research problem in itself. So we didn't have time to really focus in on that. But our quick and dirty solution was to just pay attention to the forward progress of the robot in a separate process. And if that process saw that very little progress had occurred over a certain amount of time, it would increase a factor that we called the frenzy factor in our code. And an increase in this frenzy factor would actually add more wild randomness to these motor commands, and even to the point where it would actually command the robot to even go backwards, even though backwards commanding was not even part of our normal ant behavior logic. Once we got the application software tweaked and working nicely in Gazebo, we added more simulated robots to Gazebo. We increased the number of N from 1. We also added a base station module for all the robots to communicate with. And this base station module, this base station feature included robots sending information to the base station and then the base station relaying information to the other robots. That added a layer of complexity that couldn't really be tested until we had multiple robots operating in Gazebo, or couldn't easily be tested. So we did have lots of issues to solve once we got to this point, and we're adding new features like that. We did design these robots so that they only communicate with the base station and not communicate with the other robots directly. Like I said earlier, it would have been easy to have these robots communicate with each other. I mean, they all have Wi-Fi. But we were trying to mimic this biological system, this biological ant behavior system, and their communication. So the next step was to put the software load that had basically passed simulation testing and was working in simulation, put it on a physical robot and see if it worked. And for the most part, it did. There were some differences in the real sensor data that we had to figure out and handle. For example, the data coming out of the IMU compass was a lot noisier than we had anticipated, But when we troubleshot that, we realized that the noise was actually being injected into the IMU signal by our motors. So we had to actually move the IMU farther away from the motors, and the data settled down quite a bit and became usable. Another example of surprising data, at least to us, was that the location from the GPS sensor, it drifted slowly over time. We knew that this inexpensive GPS sensor that we chose was not going to be super high resolution, and that we'd be lucky to know where the robot was, within a couple of meters. But we were surprised when we saw the data just drift slowly, 5 meters or more, over about 10 minutes or so. And this is a scatter plot showing the robot's position over about 10 minutes, and the robot was actually stationary the entire time. And the whole plot is 20 meters across, so the drift that this plot is pointing out is about 5 meters or so. But it turns out that that's just the nature of this sensor at this resolution. It's just not designed to give 1 meter accuracy or sub-meter accuracy. But we didn't actually have to go buy a more precise sensor in this case, because our Ant-inspired software algorithm and the genetic algorithm that evolved the robot behaviors was able to get these robots to perform productive work even with this degree of sensor error. The robots in the system didn't need to know exactly where they were in order to use these ant search behaviors and to find resources and bring those resources back to the lander. So this idea of performing that task with imperfect sensors was actually part of the research project in the first place. So it was actually a positive result. We didn't actually want our sensors to be perfect in this project. Some of the sensor data realness that we found in the real world, we were able to program back into the XML gazebo models in order to make the simulation more closely match the real robots. For example, a slow 3 or 4 meter drift was programmed back into the GPS gazebo plugin right there on the screen. And also Gaussian noise, the last line, made it act a little more noisy like the real sensor data was on board. There were a few other issues that kind of cropped up on us. When you start to work with real robots, one of them was battery charging, which we were not able to perform battery charging overnight due to NASA safety concerns. So that took a lot of time out of our day. We did design the robots with multiple battery packs. We had enough chargers to charge one robot's batteries at a time. So it took a while to charge all 4 robots. So that was a lesson learned. Also, the sensors and other hardware on board these robots occasionally broke on us, and we had to take time out and troubleshoot, and sometimes we had to replace hardware and solder wires and stuff like that. So once we got the individual robots all kind of working, then we jumped into testing multiple robots simultaneously. Now, at this point, it became harder to troubleshoot with so much going on at one time. We ran 4 robots simultaneously, and initially not all the bugs were worked out. And so when we were trying to track down software bugs and also hardware issues were cropping up, that threw a wrench into the whole works. This combination of software and hardware in robotics increases the challenge compared to a straight software project. When a robot wasn't doing what we thought it should be doing, we had lots of data to look at. We looked at the ROS data between each executable. Sometimes we would turn on debugging messages and have to pore through those. Sometimes the bad behavior wasn't repeatable. That's always fun. As we got more and more experience working with these robots and troubleshooting and fixing individual issues with them, we started to recognize that some of these robots' individual personalities kind of came out. An example of that is one of our issues was a robot would stop doing the expected ant behaviors and it would just drive straight forever, nonstop. They would make a run for it. They were trying to get away from us. And really driving straight for a little while is a valid ant behavior, so we didn't always notice them making a run for it right away. We did notice after a while that one of the 4 robots was more prone to make a run for it than the other. We had 4 robots in this project, and they were supposed to be identical. And since one of them was not acting like the others, this made us look really hard into a hardware problem with this one robot. This behavior of running for the hills just never happened in simulation, so there's no way it could be a software problem, right? It turns out it was a very subtle software problem. It was just a little corner of our logic that was messy, and we had never cleaned it up. And any of those robots could have ended up in this little corner of logic, but one robot ended up there more than the others because its compass data was a little bit noisier than the others, and it caused one of the robots to overshoot its target heading every time it tried to change direction and ended up in that bad code. So obviously our code was not fully tested. Anybody else ever been there? It took us a while to figure that one out and fix the bad code. But finally, when all the robots were acting like they were supposed to and no longer attempting to make a run for it, we were finally able to perform the scientific trials and collect data for the research that we set out to do. And in this video, you can see a robot starting at home, and it turns toward a random heading, and it starts traveling outward away from home in the direction of the search area that the robot chose. In this video, you can see that this robot is searching for barcodes. This is the biased random walk algorithm. The robot basically makes a turn, steps forward, makes another turn, steps forward, and continues that. The green robot in this video is about to see a barcode. He just went past him, and after he goes past him, he recognizes it. The AMP-based algorithm has the robot spin around in place to look for more barcodes in the area, and it actually counts the number of barcodes it sees while it spins around. And this total number of barcodes helps him decide whether to come back here for his next trip. It also helps him decide whether to leave a pheromone trail and ask for help. And the yellow robot at the top in this video is just making a beeline for home. He's doing that either because he's bringing a barcode home, or he gave up the search and needs to start all over again from home. When this project was all said and done, these are the parameters that, of the research trials that we were able to run. We did 19 official trials in the Gazebo simulator, 10 official trials outdoors using the real robots, and then we performed 17 more bonus long-term overnight Gazebo trials, in the simulator. The reason we needed these multiple trials on this project is because one run of these robots wouldn't give us a feel for the actual results because there's probabilities and randomness in the algorithm, so it takes multiple trials using the exact same parameters in order to arrive at an average efficiency score for this type of system. And to summarize the results, they were positive. Yay! This ant-inspired system worked very well. They found and gathered simulated food from an unknown area that was filled with obstacles. They used simulated pheromone trails to communicate with the others. They simulated robot battery charging. They worked together to increase the efficiency of the colony. And they did all this using inexpensive computers and inexpensive sensors. Now, I'm almost out of time, but something really cool that spun off that I want to mention real quick is this collegiate competition that's sponsored by the NASA Education Office. It's called the NASA Swarmathon, and the intent is to advance autonomous swarm robotic algorithms and give a boost to science, technology, engineering, and math in our minority-serving colleges and universities. So the student teams from these colleges and universities all across the US, they apply, and we allow a certain number of teams to compete in a virtual or simulated competition, and it doesn't cost them anything. We also allow a certain number of teams to compete in a physical competition with real robots, also no cost to them at all. The competing teams are given access to our simulation system, and they program their robots to find and collect these barcodes and bring them home. And the physical teams are actually shipped a set of actual swarmy robots to try their software on. And then all the teams, both the virtual teams and the physical teams, they just ship us their code. And we perform a virtual competition in a computer lab, and we also perform a physical competition in a parking lot at the Kennedy Space Center in Florida. And we execute their code on a set of house robots. And they don't even have to come to Florida for this competition. Most of the students did actually come. But it makes it very inexpensive for these universities to take part. We give the winning teams cash prizes. And we just had our first year of this competition back in April. It went very well. The NASA funding is for 3 years, and so we're planning for year 2 right now. And if it goes as well as expected, we hope to get more funding from other sources so that we can continue beyond the original NASA-funded 3 years. We've also had some interest from international teams wanting to take part, and that's also going to require some funding from a different source. This is version 2 that I talked about earlier. It has some improvements. It has bigger and better batteries, more powerful, more capable computer. All the custom mounting brackets and standoffs are really high quality UV cured, 3D printed acrylic. There's a custom designed printed circuit board hidden underneath there, and that allows all the sensors to attach using common connectors instead of those wire terminal blocks that are troublesome. And this circuit board eases the assembly, the hardware troubleshooting, and the battery charging. So we're also working on a robotic gripper system for these robots so that the competitors during year 2 can actually pick up blocks and carry them home as opposed to just pretending to carry barcodes home. We think that's going to really improve the competition and make it more real, more realistic like an ISRU mission. We think that a swarming robotic system like this that's autonomous could be useful for searching and finding and collecting precious ISRU resources on the moon or on Mars someday, and we're really excited about the biologically inspired behavior algorithms and the genetic algorithm and the potential to perform useful work without requiring a lot of processing power or memory. We're really excited about that aspect. And it would be very unfair of me to take all the credit for this project. It was a team effort, and all these team members were very impressive in their knowledge and in their dedication. I apologize, I've taken the entire 45 minutes, and I don't have time for questions, but I will be happy to talk to you during the breaks. I'll be here today, I'll be here tomorrow, and answer any questions you might have. So thank you very much for your interest, and enjoy the rest of the conference. Thank you.